Welcome learners. In the previous day, we have considered or discussed about the course outcome, syllabus, these things only. We did not enter into any specific topic. Today, we will discuss about some of the elementary signals, basic signal processing operators, and also we will also try, if time permits, the orthogonal signal space. The learners who have done my classes in the third semester and also in the fourth semester may feel bored again with the conception or discussion of elementary signals, Fourier series and Fourier transform. But what we told in the previous lecture, that Fourier series and Fourier transform or basic concept of signal and analysis is much needed to understand this analog communication. So let's start with the most elementary signal or most basic signal, widely used signal, that is sinusoidal signals. So topic elementary signal. Those who have the notes handwritten by me may follow page number 1 for his understanding. This is the basic sinusoidal signal. It is obviously periodic in nature and having a time period of 2 pi. That means after 2 pi radian, it will repeat its phenomenon or action. This is a 0, this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi. The cosinusoidal signal, how the sinusoidal signal comes, have already been discussed in the third semester, and how the cosinusoidal signal is represented is nothing but cosinusoidal is also a sinusoidal signal, but it starts from this pi by 2. That means it has additional phase of 90 degree. In the same way, after rotating 360 degree, its behavior is repeated. This is cosinusoidal signal. You know how it looks. So these are the basic. If you want to draw what is the value of cos at 90 degree, this is 90 degree, that means pi by 2. At pi the value is -1. At 3 pi by 2 its value is not 3 pi by 2, this is here at pi it has value of, this is pi, this is 3 pi by 2, and this is 2 pi. So at pi it has a value of -1, and at 2 pi it has a value of +1. And if you see, both the signals have the same waveform. Only difference, this signal start with 90 degree phase advancement. So try to understand this fact, it will be used this term, and we will use this term, the sinusoidal. When we tell that sinusoidal waveform, it includes both the sine wave and the cosine wave, because there is no such difference between sine and cosine. If you carefully find it, notice it, what you will interestingly see, say this is the cosinusoidal signal, and if we cut it from here, if we cut the sinusoidal signal from here, okay, or say from here, if we cut from this portion, or from here, you will see, now you see this is a sinusoidal signal. Or you can see, if we consider from here, the phase is changed, the waveform is like the sinusoidal signal. Therefore, this cosine and sine waveform are similar, just only the phase difference. Then comes the exponential signals. Exponential signals, this sine and cosine waves can also be represented by exponential signals. Let's first understand the exponential signal, how it behaves, or not behave, how it is represented. Say a exponent is of ej theta, or r into e to the power j theta. And from Euler's theorem, we know e to the power j theta is nothing but cos theta plus j sin theta. Now, if we take the magnitude of this exponential signal, we get what amplitude of this cos plus j sin theta is root over cos square theta plus sin square theta. That means the magnitude is r. Magnitude is r, and what is the angle? Angle is tan inverse. For a complex number, tan inverse, this is also called not only complex exponential, this is called complex exponential. For complex exponential, we have the complex part also. So this can be represented as a plus jb, where a is r cos theta and b is r sin theta. And if we take the angle theta, what it will be? Tan inverse b by a. So what is b? B is here sin theta and a is cos theta. R vanishes as it is both in the numerator and in denominator. So what is this? This is nothing but tan inverse what is this sin theta? Sin theta, if we consider r this as the complex exponential, so here we see, and if the angle is theta, theta is nothing but what? It has two parts. One is on the in this direction, which represent if and radius is r. So these represent r cos theta, this part, and this represent r sin theta. Naturally, this is our imaginary axis and this is our real axis. On the real axis r cos theta and on the imaginary axis r sin theta. So what we see, the magnitude of the complex exponential is capital R, and it has an angle theta which varies depending on its part, depending on its value on the imaginary part and on the real part, and it rotates in this direction. Now r e to the power minus j theta can also be considered in this way. So what we have seen, the complex exponential have both the part of sine and cosine, and this cosine part and this is the sine part, and it has a radius of r and it rotates with an angle that is calculated from its projection on the y-axis divided by projection on the x-axis. Now, rewrite the Euler's theorem. E to the power j theta is cos theta plus j sin theta. Again, e to the power minus j theta is cos theta minus j sin theta. From this, what we get, if we add these two signals, e to the power j theta plus e to the power minus j theta, what we get? We get 2 cos theta. Okay. Therefore, we can write cos theta equals to nothing but half plus e to the power j theta plus e to the power minus j theta. Okay. From here, we see that cos theta part has two complex exponential part. One is half e to the power j theta and another is half e to the power j minus theta. Okay. Now if we plot how it looks, this is the real part, this is imaginary part, e to the power j theta, e to the power minus j theta. If we add these two, we will get what? This real part. Therefore, cos is nothing but the summation of two exponents running in two directions, in two opposite directions. In the similar way, sine can be represented. Therefore, sine, cos, e to the power j theta, all these are one types of sinusoidal signals which repeats its action at a particular time interval, and they are interchangeable. That means we can represent a cosine signal by sine. We can represent a sine or cos in exponents, a complex exponential, and complex exponential can also be represented in forms of sine or cosine. Now we will consider, this was the complex exponential, now we will consider exponential signal whose value monotonically increases, either increases or decreases. Like consider this signal. Say this is e to the power minus 80. This is e to the power minus 80. Now, what is value? This is a t and this is function of t, ft. Therefore, we see ft is equals to 1 for t equals to 0, equals to 0 for t is infinite, and for minus infinite the value of the signal is infinite. So what you see? This is exponential signal. It is real exponential, not the complex. So e to the power minus at. If we substitute t equals to 0 here, what we get? E to the power 0, that means 1. If we put t is minus infinite, that means e to the power infinite, as there is also a negative sign in the power. So it will start from infinite. When t tends to infinite, it is 1 by e to the power infinite, that means 0. In the similar way, we can also draw another real exponential signal. Sorry, it will look like that. It is represented by, written by or denoted by e to the power plus t, which has a value of infinite and infinite, and minus infinite it converges to 0, and at t equals to 0 it is also 1. Now we will see another family of elementary signal, that is unit step, unit ramp, unit impulse, like that. At first we will see unit step signal. This is a t and this is a gt. We will use this notion gt, as in most of the lectures the function I have represented or denoted by gt. Therefore one convention should be used everywhere. So this is a t, this is gt. What is the unit step? Unit steps tell that ut equals to, rather we can write gt equals to ut here. Here the gt is represented by ut. Ut equals to 1 for t greater than 0, equals to 0 for t less than 0. Then what is the value at t equals to 0? Confusing. It starts from 0 and reaches 1 in no time. So what is the value of here, 0 or 1? Some books follows that, okay, as it has a value of 1 at t equals to 0, maximum value, take the maximum value. Therefore, they use this symbol, t greater than equals to 0. Some books do some averaging and tells that ut is 1 for t greater than 0, ut is 0 for t less than 0, and equals to half for t equals to 0. However, mostly this convention, this t for t greater than equals to 0, the value is 1, is mostly used. In the similar way, there is another function t, and this is say rt. How it is represented? This rt equals to, this is ramp function, rt equals to t for t greater than equals to 0 and 0 otherwise. That means we will not go further. We have considered for t less than 0, this is 0, and for t greater than equals to 0, its value is t. That means if t is 1, then this rt is also 1. If it is 2, then rt is also 2. That means here if we consider y equal to mx, then here m is 1. Now this part, after understanding this unit step, we can write that in another way, that rt is nothing but t. If we simply write t for all values of t, then it will be like that. For positive value positive, negative value negative. But if we multiply this t with ut, and ut has 0 value for negative value of t, therefore when we will multiply this signal, this t, with that of unit step, we will get only the positive part, which will give me the ramp function. In the similar way, there is another very important signal which is widely used in communication, that is unit impulse. We have given much time in classes regarding unit impulse to understand. The name basically was direct delta. In direct delta, what is that? It is considered a signal T and represented as del T. It has value only at T equals to 0. That means del T equals to 0 for T not equals to 0. Then what is the value at T? It is going upward. Yes, it is going upward in the direction of infinite. And in such a way that the area under the curve is 1. That means there is, if we can consider infinitesimally small area around this T, therefore it is actually drawn in this way, very small area, in this way it will go, the area under this curve will be 1. It is difficult to represent mathematically. That means del T into dt for minus infinite to plus infinite, what will be the value? It will go on. What is the value at T equals to 0? We cannot tell. But we can tell that it does not have value for T not equals to 0, and at T equals to 0 it is infinitesimally large, infinitesimally it is going in such a way that the area under the curve is 1. We can also, it has several properties. So what was the problem? That we cannot measure this one, or we cannot generate in this one. Then what to do? There is some approximation drawn in this case. This is a T and this is del T. A small area is considered here. Here the width of this is delta. So what should be the area? What should be the length of this small area? The length of this small, what we can tell, this square rectangle. Okay, the length of this rectangle we can write it as the area length of this, or height rather.